Welcome everybody. We are, as usual, waiting 2 minutes at least to start. I'm happy you are there in the AI for EU Cafe today. As you can see on my right is James Crowley, and today the theme is Artificial Intelligence, a Rupture Technology for Innovation. I hope you are in the right place with that. So I see the people filling in. My name is Carmen McWilliams. I am your moderator and cafe manager, like always. If you have any questions, you can anytime contact me via this email you see on the slide. And I'm basically organizing it and make sure that everything goes well. And I will be also the background person later to ask your questions to James. So I'm basically the assistant. And please take notice that this session will be recorded. The recording of this live web session will be available on demand. I will send it to all the participants. And therefore, no confidential information shall be shared in this cafe session. It's public. Anybody can join. And here in this cafe, we agree that if the speaker expresses his personal view and opinion. This is not the official AI for EU message of the project, but we are part of the AI for EU project. So you will find the cafe, the online sessions on the platform if you register. So, and I'm showing you another slide. We're slowly starting, it's filling in. So what is this AI cafe? The web cafe is public and offers a series of live web sessions on AI. Please join us online to gain insight into the European AI scene. You get the chance to share knowledge and experiences and meet stakeholders from various areas of AI research and applications. So I would say now it's time to introduce our great presenter today and speaker, James Crowley. Hello.
Good afternoon, Carmen. Good afternoon, everyone.
Good afternoon, James. Great to have you here. I have a short introduction about you, and then I let you start. James Crowley is a professor at the University Grenoble Alps, where he teaches courses in computer vision, machine learning, and artificial intelligence at Grenoble Institute Polytechnic. He directs the pervasive interaction research group of the Grenoble Informatics Laboratory at INRIA Grenoble Rhône-Alpes Research Center in Montbonnon, France. He has recently been named to chair the Intelligent Collaborative Systems at the Grenoble Multidisciplinary AI Institute. Wow, long names. And over the last 35 years, Professor Crowley has made a number of fundamental contributions to computer vision, robotics, multimodal, interaction, and intelligent systems. These include early innovations in scale-invariant computer vision, localization, and mapping for mobile robots, appearance-based techniques for computer vision, and visual perception for human-computer interaction. Current research concerns collaborative interaction with intelligent systems. Welcome again. Now, I think I'll let you speak, and I will hand over. This will take a moment. Everybody stay with us. I changed the presenter to James, and I do this now by saying yes. And now, James you could show your screen. Let's see, it works. I see your screen.
Okay, very good. Can you see me for just a minute if I do that?
Yes.
Okay, fine, and I'll go back to my screen in a second. So good afternoon, everyone. Welcome to this webinar. Over the next hour, well, in the next 40 minutes or so, Carmen has asked me to talk about how artificial intelligence can be used to generate technological rupture across a wide spectrum of technologies. And so we'll look at that. Now, what I've prepared this afternoon, hold on, let me do this right. Yes, does that look good, Carmen?
Yes.
Okay, very good. What I've prepared is just a few words about what we mean by intelligence and artificial intelligence, going back to Turing, because I think Turing gave us actually a very good definition. I'll say a few words about the evolution of paradigms for AI and the barriers that kept AI from fulfilling its promise as a really enabling technology across all technologies. And how we've been able to overcome those barriers in the last 5-10 years or so, and then the potential for innovations that opens up. I'll give some ideas about how to look for areas where AI can really make a difference, but also talk about some of the current open problems that people are working on and my own view on how we can address those problems or why they're difficult. Okay, but let me start with what I mean by intelligence. So Turing gave us actually a very nice, simple, easy to understand definition of intelligence based on behavior. Okay, behavior is the actions and interactions of a system. And when we say a system is intelligent, we're giving a label to it. And Turing told us that we could test intelligence with something he called the imitation game. That is, you sit a human down at a computer terminal and have him interact with another agent, and he doesn't know whether the agent is an artificial agent or another human. He's separated by a barrier. And if the human cannot tell the difference between whether the other agent is a human or an artificial system, well, then we can say that the artificial system meets his definition for intelligence. So we can boil that down to human level performance at social interaction, because the way you win or lose the Turing test is really to try and trick the other agent with social questions. Computers were pretty good at answering factual questions, but when it came down to social interaction, not so good. Now, in modern terms, we can generalize that because we've got technologies not just to interact with people, but also with other systems and with the physical world. And in particular, many of the innovations that are possible happen when we take this technology for interaction that we're going to talk about and apply it, not just interacting with people, but also with the world or with other systems. So let me give a general definition of human level performance at interaction. Very simple. Okay, and it's understood that generally that requires using perception, action, communication, and/or cognition. But basically, we're qualifying interaction as intelligent or non-intelligent. And we're talking about new technologies that make it possible to build systems, artificial systems, that can meet Turing's definition for intelligence. Now, this domain actually is quite old. Really, the name artificial intelligence came out of a pioneering symposium at Dartmouth in 1956, at which a number of the early pioneers got together and sort of decided to found a new research field. Among the people, influential people in the area were Arthur Samuel, who invented a learning checkers game, John McCarthy, who really was responsible, well, gave us Lisp programming and very much was responsible for the turn to logic programming in the 90s in AI. Marvin Minsky, who gave us formal representations for knowledge with his frame system that's still widely used. Herb Simon, who insisted that AI and cognitive science were intimately related and pushed AI to use concepts for cognitive science and to provide context for cognitive science. And Alan Newell, who insisted very much on planning and problem solving as the way to get at intelligence. So AI really became a convergence of cognitive science, logic, planning, pattern recognition, image processing, and some other related fields in the 1950s. And if you look back prior to Dartmouth and asked people what was artificial intelligence, they would say, well, the technology is automata, finite state machines, or pattern recognition. After Dartmouth, the community turned increasingly to planning and problem solving. Newell convinced everyone that problem solving was the core to intelligence, and in order to get a handle on problem solving, we could formalize it as a planning problem, and this became the dominant problem in a lot of AI work in the 70s and 80s. In the late 70s, we saw emerge a new class of system called expert systems. And these created quite a wave. In fact, a lot of investment went into AI in 80 to 85. It was the hot topic. A lot of AI researchers became very rich, but then didn't live up to its promise. Meantime, the scientific community turns towards logic and logic programming, but found that that was very limited for a number of reasons, and turned increasingly to machine learning with Bayesian methods and the semantic web. But throughout all these epochs, three fundamental barriers appeared. Firstly, for anything involving pattern recognition or learning, there was insufficient labeled data for learning. There was insufficient computing power. In particular, up until the 90s, we just didn't have the power to do anything reasonable. And the big barrier was the prohibitive cost of encoding domain knowledge. This is what killed expert systems in the 80s. For example, consider the myosin antibiotic therapy advisor and its generalization E-myosin that was sold by Feigenbaum and his group at Stanford. In that system, a domain expert would work with a software engineer to build the system, and the big cost was in building up the domain knowledge. Very big cost. Years, man-years of work would go into building domain knowledge, and just couldn't be justified with the results that the system was providing. Okay, so there was a lot of interest in the potential power of the systems, but the barrier was the prohibitive cost of generating the domain knowledge for such a system. So three fundamental barriers: training data, computing power, and domain knowledge. So what's changed? Well, over the last 10 years, over the last 10 to 15 years, we've seen training data emerge from planetary scale connections on the internet and the World Wide Web. The internet was the game changer because it has just provided us with massive volumes of data and continues to. The World Wide Web because it allows people to crowdsource and come together to build massive data sets. Computing power, well, we've gradually caught up with Moore's Law, doubling every 18 months over the last 50 years. And in particular in the last 15 years with the emergence of GPUs and more recently cloud computing supercomputers that are available to everybody over the internet. For knowledge, however, the big rupture was deep learning. Because deep learning has given us a way to exploit all of human knowledge in generating domain knowledge. And that's really where the innovation is coming from. But we need all three: planetary scale data, cloud computing, and deep learning. So deep learning has really triggered a major scientific breakthrough. It's been found to provide reliable solutions to long-standing problems in perception, problem solving, and as I'll show in a minute, also in synthesis. So it's enabled AI to become a rupture technology, but really by the convergence of deep learning with supercomputing and planetary scale data. The impact on human society is expected to be on a scale comparable to electricity or the printing press. Massive. But like with electricity and the printing press, it'll take a century or so for this all to play out. Well, when we talk deep learning, in fact, the technology's been there since the 50s. Now, one person who was not invited to the Dartmouth Symposium was Frank Rosenblatt. Rosenblatt invented what he called the universal learning machine, the perceptron. In 1958, he built a machine to do the perceptron. The perceptron was, in fact, a system or an algorithm for learning linear decision surfaces. It was, however, somewhat limited. It could only learn to classify patterns, in a particular, well, it could only learn to classify patterns. It required labeled training data, and the data had to be linearly separable. There had to be a linear decision surface that separated the classes for the data. If the training data was not linear separable, the algorithm would loop infinitely. It would never converge. It would not terminate. And there was no way to know until there was no way to know in advance if the data was going to be separable or not. So these barriers led a number of people, and Minsky in particular, to strongly criticize the perceptron, to reject the whole approach, and to make it taboo in artificial intelligence for many years. However, a group of people continued to play with the ideas, and in the 70s, we saw emerge an algorithm called backpropagation for learning for training neural networks. fact, the real innovation that made backpropagation possible was the replacement of the hard decision surface in the perceptron, the step function, with a soft decision function that had a derivative. This allowed us to do gradient descent to train the network, to train the weights of the network. Okay. That gradient descent could be expressed in a simple distributed algorithm called backpropagation, invented by Werbrus in, I think it was 1976, and championed by people like Rumelhart and Hinton and others back in the 70s. And suddenly, neural networks provided simple solutions to what were really hard AI recognition problems that couldn't be solved with traditional expert system type solutions. However, the solutions were difficult to reproduce, and the cost of learning in terms of data and computation would grow with the number of hidden layers. Okay. So there was a brief flash in the pan from 1980 to 1990, maybe 85, where artificial neural networks were hot, and then they were not. They were superseded by other techniques which were better understood, more easily mathematically modeled, etc. However, people continued to play with these techniques, and for example, in the 90s, Jan LeCun came up with a number of architectures that he called Linnet. The fifth architecture, Linnet 5, won the competition for recognizing handwritten numbers on checks, which was a notoriously hard problem in machine perception. Curiously, the machine learning and computer vision communities completely and consciously ignored Linnet and similar systems. LeCun could not publish his results. However, people continued to play with deeper and deeper nets, driven by more and more data. And in the 2000s, we saw emerge a number of benchmark data sets for machine learning. At the time, the dominant paradigms were support vector machines and things like that, until Alex Krzyznicki and Jeff Hinton dramatically won the ImageNet Large-Scale Visual Recognition Challenge in 2012 with dramatic gains in error rate. Okay? This triggered a paradigm shift in computer vision, in speech recognition, and in machine learning, and rapidly afterward, and more generally in all of AI, towards deep learning. Now, there are a number of networks that are popular today. Many people talk about Inception or networks like that. My favorite right now is the workhorse called VGG that was proposed by Andrew Zisserman and Karen Simoian at Oxford. VGG stands for the Visual Geometry Group at Oxford, which was traditionally a very strong mathematical group at Oxford. And they produced a simple, reliable, and very general workhorse that they called VGG. And they published it. Where they published the data, they published the source. So you can download it from GitHub or TensorFlow or program in Keras. It's actually fairly easy to reproduce in Keras. I have my students do that as an exercise. Okay? And it's essentially a system that takes a 224 by 224 by 3 color retina that you can put anywhere in the image, runs it through a number of layers, and produces an output vector of 1,000 weights, which stand for 1,000 trained object classes. And what's really powerful about this is that we can do transfer learning. We can take a network trained on one data set and easily adapt it to another data set. So train it on, for example, foodstuffs, and then we can take it and look at cancer cells, which is a really surprising result that we've had in our own group in the last year. Okay. You train it on one, take networks trained for one thing and adapt them to the other. So you don't need so much learning data to be able to use this network. The other thing is it's fairly easy to use and reliable. It may not be the highest performance for every problem, but it's one you can easily have your undergraduate students program. Now, one of the amazing things that people don't realize is that these networks are not only good for discrimination, they're also good for generation. You can turn the network around. So classically, the network takes an input vector of features, X, and maps it into a class label, Y. However, we can go backwards. We can take a class label, Y, and map it into an output vector, X. And that output vector can be spatial temporal. It can be a pattern. It can reproduce natural sounds. It can reproduce natural language. You can generate synthetic images and synthetic image sequences. You can do animation. You can do realistic talking heads. In fact, this is being used now to produce deep fake. So be careful what you see on the internet. Some of it may actually just be artificially generated. it can be used for a number of things. For example, we've used VGG in an hourglass model to see where the object classes are in an image. We just turn it around, take the weights, and we can poke into that vector of 1,000 classes, say, okay, I want to see where the bicycles are. And it'll light up for us the cells in the original image that contributed to bicycle. We can also do other things. We can take one network that's trained to discriminate on the left and use it to generate output patterns on the right. So we can do discrimination and generation together to do things like make stimulus response systems. In fact, right now, this year, last year, the current really hot topics include something called generative adversarial networks. General adversarial networks get around the problem of requiring labeled training data by having a generative network and a discriminative network compete with each other, each one trying to fool the other, each one training the other, and each one making the other better. Okay, and that's resulted in some amazingly powerful systems. We also have deep reinforcement learning, where a network can continue playing a game, for example, or working in a domain and getting better and better. The system AlphaGo that beat the world champion Go players was trained with deep reinforcement learning. And increasingly, we're seeing a convergence of deep learning and cognitive systems, so that we can combine the deep networks for perception and action with things like cognitive computing for reasoning and natural language expression. Now, one of the barriers that many people cited for a while was that this is all fine for numbers, but we need to handle text. Yes. Well, it turns out there's an algorithm called Word2Vec, which will take words and map them into vectors of context. This works essentially by word frequency counts. Any document or any paragraph is a context. And you can count the word frequencies and determine the relevance and the information content of the words, and then project that onto a context vector. And you can compare context vectors with cosine angles. And it turns out similar contexts are related, so that you can understand what something is about by looking at the collection of contexts that come up from a set of words. What's amazing is this can be used with deep learning. So we can take any text, project it into its context vectors, and then put that into a deep learning network. And this is the technology that's currently being used for chatbots, but it can also be used for data mining knowledge on the internet. Here's an example of a chatbot. I downloaded this from the internet last week. It's a weather bot, and it starts up with, "Hi, I'm a weather bot, what's your zip code?" And of course, the person is liable to say anything like, "What's your name?" "Okay, my name is Weibo. Can you tell me whether the weather in other zip codes?" "Sure, type in the weather in X." "What is the weather in New York?" "It's 76 degrees. 76 degrees and sunny." "Cool, nice to meet you." Well, this was somebody else's example, so I went off and did a Google on chatbots and found this thing called Cleverbot and typed into it, "Good afternoon." And it answered, "Good afternoon. Tell me about yourself." "Well, I'm planning to do something big." "What kind of big thing do you plan?" "I'll take that as a compliment." Well, you can see that something's a little fishy in the answer, really. He doesn't really know what I'm doing. He's just giving me nice responses to my question. Chatbots don't really understand the conversation. It's often possible to fool people, but they're really stimulus response systems, like a parrot or a zombie. And they're not a solution to the Turing test. You put a chatbot into the Turing test, and you can pretty rapidly discover that it's not intelligent. It's not something you would call intelligent, but it does generate a reasonable response. And if you stay in its domain of expertise, you can get information from it. And that's right now something that's very hot on the internet, of companies providing chatbots to inform their users. Now, something I saw very interesting last week, and I didn't make slides to present it, was one of my colleagues using this technology, using machine learning, deep learning, to go not into simply an hourglass chatbot, but into logical forms that he then put into a logic programming system to do genuine logical reasoning, and then using the output from that back through another network to generate natural language responses. So there is some hope that the technology could give us a portal into reasoning systems. And that, in fact, is the promise of cognitive computing. In cognitive computing, a group of domain experts called curators come together and collect and sort and select domain references like textbooks, sort documents, reference books, things on the internet, etc. They then feed these into a system as domain knowledge, which are interpreted and used by cognitive architecture, and which can generate a cognitive AI program which can act as an intelligent advisor. And this has very real applications, lots of generation of wealth in domains like medical, legal, and financial. In fact, IBM is marketing this under the name Watson. IBM is one of the champions of this. This is a slide that shows how IBM Watson works, taking the corpus that the curators have assembled, compiling it down into a structure that Watson can use to answer questions, generate hypotheses, score the hypotheses as evidence, come up with a final ranking, and then answer. And as you all know, Watson won the Jeopardy competition, but is now being marketed as an expert or as an enabling technology for building experts in many domains.
My name is Pepper.
And here's
I'm a completely new species of social humanoid
Watson with
robot
Pepper.
designed by SoftBank Robotics. Now that I'm using Watson, I am learning a lot. I can read up to 800 million pages a second and can better understand humans' natural language.
Okay, very impressive.
That, by the way, is not
Yay,
scripted.
It really is. See what I did? I was able to recognize your tone and understand that you're excited, so I responded enthusiastically.
All right, well, that was an interesting video that came out of CES, but that's the kind of thing you can do, putting Watson and cognitive computing in the background behind machines. And in fact, one of the views right now is AI as a service on the cloud, taking cognitive computing on a cloud computer, and it is computationally very intensive, and connecting it over the internet to your TV, your smart speaker, your personal robot, your smart refrigerator, your smartphone, etc. In fact, running all the smart appliances in your house from a cloud computer. There is a small problem with privacy and trust. We'll get back to that. So what's going on here? Well, classically, when we build a system in software engineering, we'd run something like the classic V cycle of software engineering. We specify requirements, do a design, do the implementation, do functional testing, and then do requirements testing. And the result was a program created by an engineer who knew how the program worked. It was created by a team of engineers. That's not how machine learning works. In machine learning, we take a machine learning architecture chosen by an engineer, which may or may not be there, and then run that with training data, which can come from enterprise data, the internet of things, crowdsourcing, or any source. Run that through the machine learning algorithm and produce an AI program. So really, with machine learning, the data becomes the code. And this raises two fundamental problems. There's the problem of verification. How can you certify that the resulting AI program will have correct behavior? There's also a problem with explanation. How can you explain the output from the network? So, can we use machine learning and AI to enable technological rupture in different domains? And what are those potential domains? Well, there's a very interesting answer to that question that came from a book by Kai-Fu Lee. Kai-Fu Lee was one of my colleagues at Carnegie Mellon when I was there in the 70s and 80s. Went back to China, and I believe he ran Google China for a while, and then he became an angel investor in China. And he wrote a book last year where the slogan was, AI is the fire, data is the fuel. To predict AI innovation, look for the data. He predicted 5 waves of rupture from innovation with AI. On us now, currently happening, the first wave has to do with internet AI and AI as a service. And in this domain, US and China compete. They both have access to good computing, good data. Europe has fallen behind. The Americans have a distinct advantage in what's called enterprise AI, because since the 1970s, they've automated all the bookkeeping and management of the corporations. So everything is digital for the last 30, 40 years. You can put that into an AI learning system and actually data mine it and learn how to optimize your enterprise. The Chinese don't have that record of digitization of their corporate culture and don't quite have the data to do that. On the other hand, China jumped really quick on smartphone economy. Everybody uses a smartphone and they use it to pay for things. They use it for everything. So right now, mobile AI using smartphones and using the data collected by smartphones, China is leading, and they're accelerating their lead. What's coming next? Well, we should start to see ubiquitous perception and interaction. It's starting to emerge in China right now as a way of controlling populations, which is quite scary. We need to be attuned to that. But in general, putting computer vision, robotics, putting vision, action, interaction, and cognition into everyday objects should be increasingly possible. In fact, we do that in my group for the last 5 years. And the prices for some of the systems we build, like intelligent coffee machines, intelligent refrigerators, are really quite reasonable. Just for a few tens of euros more, you can make your system into a smart system. Beyond that, the holy grail is autonomous AI systems, really totally autonomy, and we're not there yet. In fact, we're quite far. So if you want to look for where are the potential innovations in AI, my advice is look at the interaction. Interaction with the physical world, interaction with people, interaction with the internet and with other systems, and interaction with technology. And the low-hanging fruit will be there where there is data, where there's data for interaction. Okay. Now, for example, with the physical world, there's a lot of investment right now into equipping automobiles with sensors and actuators to make them increasingly autonomous. However, adult supervision is required. We're not replacing people. We're enhancing their productivity. We're enhancing and not replacing people. We will see increasingly automated processes, but there's always a human in control and a human who's responsible. Similar situation in manufacturing. We're not seeing totally automated factories. We're seeing robots helping workers to become more productive, doing the work that's more, in French we say pénible, painful, not enjoyable, and making the work more reliable, more productive, and more enjoyable. Human environments, we can also automate things by adapting to human comfort with things like Nest or with the Roomba robot. But always adult supervision required, at least for the foreseeable future. When we interact with people, we can distinguish certain classes of devices, which could be useful. I refer to one class as advisors. These are systems that propose courses of actions. They're completely obedient and they do not act. They avoid unwanted distraction, but they offer advice and information. Your GPS your GPS system in your car is a good example of an advisor. We also have effectors. These are devices that inspire affection. They may be robots, they may be simple devices that make cute noises, but they go into your life and cheer you up. They inspire affection, they inspire pleasure. And there are other devices, which I'll call media, which extend human perception and experience. The navigation system also does this when it shows you traffic on the road. If you open up Google Maps on your computer, in some sense you're opening a media, which allows you to see where the traffic is and where the roads are crowded or not crowded. The same kind of thing, seeing weather, seeing other information about on a planetary scale. Okay, we can make these into devices that are peripheral and can interact, but don't distract. I want to talk particular about a certain class of systems that I call collaborative systems. Perhaps because I'm biased, perhaps because this is my area of research right now. Collaboration is a process where two or more actors work together to achieve a shared goal. And so collaborative intelligence systems are systems where one of the actors is a human and the other is a machine. And to be effective, they have to work as partners. To have a common goal, they have to have shared understanding of the abilities and respective roles of each other. Okay, so ideally, we'd like to build systems that assist an expert at complex critical tasks, that provide assistance and advice, but don't get in the way, that can monitor actions and attention, warn of problems, anticipate the problems and give warning, and could also perhaps perform delegated tasks, but always under human supervision and human control. Current examples include a virtual co-pilot for your car or your airplane. Maybe hand over control to the co-pilot driving down the highway. Take the control back when you're in the city. We've been asked to do a radiologist assistant that helps radiologists to make more reliable diagnoses of radiological images. I'll show in a second an example of an intelligent tutor that teaches. We can imagine a legal advisor that gives advice about legal situations, or a financial advisor, etc. In all of these systems, the human retains control and responsibility, and the system provides assistance and empowerment. So the intelligent tutor, for example, this is work common with the Education Sciences Laboratory here in Grenoble, includes a battery of sensors that watches a person interacting with an interactive screen, touch screen, in order to learn some subjects such as mathematics. So we can monitor awareness and emotion from eye gaze, from speech, from posture, from face expression, cardiac rate, etc., and guide a student through the process of concept formation, allowing them to develop their problem-solving skills. In order to do this, we have a number of research challenges we're addressing. We need to understand and interact with humans as individuals, adapting to their abilities and limits and complying with their social, ethical, and cultural norms. We need to provide information and services that's synergistic and does not disrupt. And the system needs to be explainable, accountable, and compliant with ethical, legal, social, and cultural values. And these are all important challenges right now. Now, you'll hear a lot about explainable AI right now, and part of that's driven by the GDPR, which has two volumes. One has to do with privacy, and the second one has to do with explainability. So there's a legal requirement right now that algorithms explain their decisions. The Commission, the European states are required to pass laws that make people who use computing and intelligence provide explanations for why. But in fact, if you scratch the surface, there are several different AI explainability problems. One of the problems is to explain the output from a deep network. This is the hard problem we've had with neural networks since the 80s, or even back to 50s, is to know why the network does what it does. The network is a black box, and you can't really explain what's in it. Well, it turns out that if you go back and look at the activation energies, we can imagine ways to extract information from the network, which would allow us to construct an explanation. There are a number of people working on that now, and I think we'll see those kinds of systems emerge in the next 2 or 3 years. Similarly, if you have a cognitive system or an expert system giving you advice, you're now required to be able to explain the advice. And this goes back in expert systems to the 80s. The old myosin system was required to answer questions like how and why, and to generate that from its reasoning. Now, we could do that with myosin because all of the reasoning was symbolically encoded. Not so easy when it's a deep learning system, but we're working on it. There is, however, another explainability problem that is a scientific problem. We don't know today why one deep learning network architecture is better than another. Most of the networks have been generated by experimentation. People run Python scripts and take variations on the hyperparameters and compete over a wide range of hyperparameters and just publish the network that works the best. That's no way to do science. We know what works, but we don't know why. So there's a scientific problem about knowing how to predict and how to generate deep learning networks for different problems. And that also, I predict somebody's going to make a general theory about deep learning, but we don't have it yet. So let me say my personal view on explainability. An explanation is a reason for an action or for a deviation from expectation. You can ask someone to explain why they took something, why they did something. You can ask, why did the sun rise? Why is it raining? The answer will be a form of narrative. Humans provide narratives as explanations. A narrative interprets a sequence of events as a story, placing the events in a context which gives background information which was not in the events themselves. So human narratives are often generated after the fact. You ask somebody why they did something, they don't know, but they invent a reason. They give an explanation. They're often simplistic or just plain wrong, but they're credible and thus believed. So explainable AI will require us to generate credible narratives to explain actions, decisions, and consequences of systems. Unfortunately, what's credible is not always what's true, so beware. A deeper problem is certifiability, verifiability. In classic systems, if the system were a critical system, there was a certification test. The system had to meet this verification. Not so much with deep learning. If you're training the system, especially with deep reinforcement learning, it's learning by interacting with the problem. How do you certify it? The AI program is a black box. You don't know what it's going to do. You don't know what its specs are. How do we test it? Well, I think one approach would be to look at how we qualify humans. We give them a set of tests. We make them pass with a certain score on a certain number of tests. But the way we qualify humans admits that there will be failures. We allow errors. We're not going to allow errors with our machines. We're much less tolerant with machine errors. So there's a very real problem right now about how to verify behavior and how to certify critical systems. Behind that is trustworthy. How do you know if you can trust a system? In fact, people are very bad at estimating the trust of their system. If you ask people if they trust their technology, their smartphone, their car, their food and beverage, most people will say yes, when in fact, these are the least trustworthy systems they have. You ask them about their financial services or their bank, well, they're a little bit more less trusting, but in fact, that's generally where things are more secure. To be a trusted system may be insecure and not private. To be really trusted, it needs to inspire confidence that it's secure, available, and private. In fact, the high-level expert group, the AI high-level expert group at the Commission, issued a document on trustworthy systems, and it said the systems must be lawful, they have to respect all applicable laws and regulations, ethical, respect ethical principles and values, and robust. From a technical perspective, taking into account the social environment. So essentially, they need to be controllable, safe, robust, private, transparent, and accountable. And we need to be careful with AI systems, especially intimate AI systems like personal robots and smart houses, because anything that's digital can be shared, and you don't know. You don't know when it's shared or why. So that was my brief panorama of how AI can provide a technology for technology rupture across a wide variety of areas. We looked at Turing's definition for intelligence. We reviewed briefly the evolution of paradigms for AI, the barriers and enabling technologies, and then talked about potentials for innovation and some open problems. And so I think at this point, we should open it up for questions. Carmen?
Yes, do you hear me?
Yes, I hear you fine.
Great. I have questions already for you ready, but I want to ask everybody to also put in questions. There's a question panel on the right side. You can type it in, or you can even raise your hand, and then I can even unmute you if you want. So feel free to ask questions on the right side. I'm going to read the first one of the one which is already there, which is basically, you can also say from which organization you are if you like. You don't have to, it's up to you. So the first person who asked the question is Regis Hamelin. She or he, I don't even know, wants to know, are we ready for all the innovations listed which you had in your PowerPoint, like advisors, effectors, or are there yet any technology gaps?
Oh, of course there are technology gaps. There are many technology gaps. That's why we do research, right? What I'm sketching here are things I think are attainable in the next 5 to 10 years. Okay. Now, and just because you can do it in the laboratory doesn't mean that you can sell it. So there's a technology readiness levels that have to be mounted with these things, but these are indicative based on things that we know how to do in the laboratory today. Okay. This isn't something you can go down to the local store and buy, but these are the things that I think you will see emerging if people invest in going to the technology readiness levels and getting to product. These are the things these are the things that look potentially ripe for investment. So I hope I've answered the question.
Yes, I think so. And else, Regis, please just say if you have further questions. I have another one, and this is from Annibal from Cartif. Why do you think that AI integration is still low in industry? Is it because of lack of data, lack of trust? This is from Annibal Renaud-Ness.
Well, I found two ways to interpret that question. But one is that AI investment is high, and why do I think it's low? And the other one is, can I explain why it's low? So I'll explain why it's not quite at the level we think it may eventually be, but it's coming. And part of it is just the nature of industry. When you build an industry, you make an enormous investment, not just in your product, but also in producing the product. And changing that investment costs more investment. You're throwing away the previously invested money. So much of this technology evolution will resist until people need to replace machines. So it's gradual. Now, it gets accelerated when competition happens. So if I've invested in producing my widget, and I have a widget producing machine that's going to work for 20 years, and somebody comes along and produces a superior widget and goes on the market, my widget producing machine that I so much invested in is now obsolete. So if I want to stay in the widget business, I've got to do a new investment to compete with the new machine. Okay, so they've just made my previous investment worthless, or worth much less. Okay, fortunately, ideally, I have quite a bit of enabling technology that I can build on to make my new machine. So companies will resist new technologies while they have a dominant position with the current technology. Okay. They're not always the one that are going to invest in the latest hot thing, unless they're in a competitive situation where they have to outcompete somebody who's ahead of them, and then things change. So I would explain the slow take-up by industry partly that way. Just there's an enormous investment in this industry already, and it's going to be evolutionary as these technologies work their way into industry. But what I do think is that the people who understand how to do this investment properly can make a lot of money. These are rupture technologies that will make other people's investments obsolete.
Mm-hmm.
Okay?
Okay, thank you. I hope this answered the question. It looks like, as I don't get new question. I also don't have anybody raising his hand. There's basically, in the panel of attendees, there's a hand. If you really want to talk, you can. I have another Francesco Kinsley. He's from Switzerland. He has a lot of questions, but we.
Greetings, Francesco.
We take one. So, and the other we can also answer later in email. When trying to find out in the industry who's actually using deep learning-based technology in production, you end up with little use cases in production. Could you give us examples of actual use cases in industrial real-life applications? Do you get this?
Well, I'm assuming you're inferring manufacturing industry. Mm-hmm. Because if we're going to talk about industry in a larger sense, you have to think about commerce. Mm-hmm. So my big example would be Amazon. Okay, now Amazon massively invests in AI, and they're using it to make optimized commercial processes for selling things that just make totally obsolete classic commerce. So yeah, that's an example of how AI is revolutionary rupture for technology is with commerce, Amazon. We could go further. We could look at many of the social networks. For example, Facebook was a very early pioneer in using deep learning and AI to mine user data to provide opportunity for publicity. Okay, and in fact, there's a whole industry now about learning about people's preferences and their choices in order to sell them or send them publicity, in order to sell them things. So these are two areas where the data was prevalent, the data was available, and the financial people jumped on it and made a rupture technology using deep learning. Where else? Well, in anywhere related to customer service. You will notice more and more for the last 2 or 3 years, chatbots. If you go into your local company and you want advice on how to do something, perhaps you want to cancel a service, perhaps you want to know how to upgrade, buy a new service, you'll deal first of all with a chatbot. Similarly, if you call the helpline, the hotline for many companies, you now get a chatbot. Okay? And you have to talk to the chatbot for a while. And if your case is really, really extreme, maybe you'll get to talk to a human. But most likely, they're going to try and get you to talk to just the chatbot that's going to give you their simple answers to most of the user problems you have. Your internet service provider will use that to help you configure your internet service or your smart TV or whatever, for example. So the commerce, okay, publicity, interaction with clients. These are 3 areas where machine learning and deep learning have been revolutionary already. What else do we see? Well, we're going to see, I really think, increased optimization of manufacturing. Because with all the enterprise data that's available in different companies, there's lots of opportunity for corporate optimization. Okay? And it's not just in the way you manufacture the widget, but the way you buy the supplies for the widget, the way you do the logistics, the way you do storage, and the way you organize the entire process. Okay? And some radically new organizations may well emerge from doing machine learning on corporate data. Otherwise, we'd go back to Kai-Fu Lee, and where there's data, there's potential for innovation. Okay? So it's not the dramatic case of the totally automated factory or the self-driving car that's the most prominent and the most immediate. Those may come later, but in the meantime, it's wherever we can find lots of data, we can profit from that data and turn it into knowledge and use that to generate innovation.
Thank you. Thank you. Now we're doing a real experiment because Umar Shah, he raised his hand and he wants to ask, I think, a question. He also wrote it, but let's try it. Let's see. Shall we do it? Let's try it, if it works. Umar? Hello?
Hi. Can you hear me? I'm female, not male.
Yeah, I'm sorry. This is really bad with me, with knowing.
No, it's okay because the name is not Anglo-Saxon, so it's not obvious what I am. I'm female.
Great, thank you.
Do I read my question out? Sorry to clarify. Do I read my question out?
I can read it. Shall I do it for you?
Yes, please. Yes, please.
Let's hear Seema read it.
Yes. I read it, yeah?
Yeah, sure.
Okay.
You. Who wants to read? James says.
Basically, when I was on Alan Turing, because I have a self-funded PhD on the Turing test, it was very difficult to find somebody to supervise. But luckily, Professor Kevin Warwick at Reading University agreed to supervise me. So in Turing's 1950 paper, he's not defining intelligence. In fact, he's very awkward in showing that if you define a word, you use other words to define the words. You get circular, like as Plato described in Laches and as Quine showed. So what Turing, for his imitation game, the category was that if a machine can answer any question in a satisfactory and a sustained manner, those are the 2 words he used. Now, I say to you, Professor Crowley, some chatbots today are much better than politicians. What is your view?
Yes and no, yes and no. Okay, yeah, thank you. It's been 40 years since I've seen that paper. And so my impressions of the Turing test may have been deformed. So thank you for reminding us. Yeah, answering questions in a satisfactory manner. There are politicians who are currently answering questions with total nonsense, providing credible narratives that people believe. And sure, the chatbot is probably more honest, but it's down to who gets the votes. I'm sorry. So you can transpose that onto whichever national politics you're thinking about.
UK general election.
Yeah, that's right. A general election, for example, but I was actually thinking of U.S. politics, but you can probably apply this to almost any country in the world. Yeah, because politicians often are in the business of inventing narratives, which are credible but not very honest. Okay, which actually manipulate opinions for a particular reason. Okay, and whereas the chatbot doesn't really care; it's just going to imitate. But let me mention though one very interesting experiment that was done with chatbots. A few years ago, I believe it was Google put on a learnable chatbot that learned from its interaction with people. I think it was Google. Okay, and people just, or maybe it was Microsoft. People discovered very quickly that they could be mean to it.
Oh, Tay, Microsoft Tay.
Yeah, Microsoft, that's right, right. And within 48 hours, the system was totally nasty. Okay, people trained that system to be nasty. They thought it was funny to train it to be nasty, and Microsoft had to take the system down because it was quite socially inappropriate what the system was telling people when they came on, and that was because of the way people interacted with it. So this is a resonance between the population and an individual, and sometimes that has nothing to do with rational behavior.
Thank you. Thank you.
But thank you for your reminding us of the actual terms of the Turing test as he proposed it. It wasn't just social interaction. It was really about answering questions.
Thank you.
Thank you, Mark. Hey, James, are you ready for more questions? It's up to you. You have 3 minutes more.
I actually have a visitor from a local company who wants to see me at 4 o'clock. So we said this would be an hour, and we've got 3 more minutes. So let's see what's in the bin.
Yes. So I would say, because it's 3 minutes to go, there are many questions out there. There are also hand raising. It's a very vivid discussion. I'm very happy. But I will now close it. I will send the questions to you, James. If you feel like you can answer.
Oh my. I've got courses to teach and deliverables to write and reports to write and a thesis to review, and you can have me answer questions. Okay. Well,
but we can maybe invite you back next year. Maybe next year I can invite you again. So let me take it back, because as we said, it's until 4 o'clock. So I will now take back the presenter, because I will basically announce the next one.
Can I say thank you, Carmen?
I want to thank you. Thank you, James. No? Thank you, super. And please join the cafe again. People want to discuss. And I'm now showing the screen, which is basically here. And now I'll show the last screen, because one moment. The next, this is what I want to say before it's getting now to the end. Join us next week again at 3 o'clock, this time with Pierre Pleven. His title is AI Opportunities and Challenges. The idea is to basically do every Wednesday at 3 p.m. a web cafe. And if you're lucky, we can continue. It depends on you. We need speakers and great topics and participants, so please join. And it's very important that you check once in a while the AI for You platform. Soon there will be also an agenda, a program, everything will advance, and then you see what's coming up next week, which kind of cafe. Meanwhile, I will inform you by email all the time, and you can also have a recording of this session per email if you like. So once more, it's now 1 minute to go. I thank everybody out there listening to us and participating. Please join again. Please also become a speaker. And thank you very much, James. And I will now end the session, and I will clap. Thank you. Bye-bye. Bye-bye.